Hi there, today we will present our ODE project as we said at the midterm presentation. We are Group 19, so let's start from the introduction of our team. Our team members are Jin Yu Lee, who is responsible for solving technical issues, Dao Ting Chen, who is responsible for circuit design and validation, In Hao Sai, who is responsible for platform construction, and Dean Lee, who is responsible for video producing. Let's explain our plan. We divide our plan into 4 topics to make the project more comprehensive. At first we will introduce our main components in our circuit, then recall the mechanism of RC circuit as we talked before. We will also explain our circuit design and introduce Raspberry Pi. Second, we will talk about how do we set our environment to run our program. Third, we will show some pattern of our code that we run on the Raspberry Pi, explain the interface. Fourth, we will introduce GPIO API and talk about how do we set the pin mode on Raspberry Pi. Last, we shot a video to present our project. Recall our plan, as we said at the beginning. We will using Raspberry Pi to power on our square wave generator and differential circuit, then the output signal will connect to a LED and a GPIO pin to make a small clock on Raspberry Pi's monitor. So we can make a digital clock by RC circuit and single board computer. The components that used is an E555, LM358, 47 microfarad capacitor and 68 kilo-ohm resistor. NE555 and LM358 is important components, so we will talk later. NE555 is a multivibrator. We can use the 555 chips for basic timing functions, such as turning a light on for a certain length of time, or you can use it to create a warning light that flashes on and off. And we can use it to produce musical notes of a particular frequency, or you can use it to control positioning of a servo device. Here is the prototype of parts of our circuit. By the differential equation that we induced before, the voltage of capacitor will charge to 2/3 versus Cc, then make output at low level and let internal transistor on, so the voltage of capacitor will discharge to 1/3 versus Cc, then make output at high level, and the internal transistor off the capacitor starts charge again. So we construct a square wave generator. The LM158 op-amp consists of 2 independent, high-gain, internally frequency-compensated operational amplifiers which were designed specifically to operate from a single power supply over a wide range of voltages. Here is LM358's pinout. We just use one op-amp. To make our signal more detectable, we add a differential circuit. BO will be IR multiplied by R, and IC will be C multiplied by derivative of B in with respect to T, since IR equals to is, BO equals to RC multiplied by derivative of B in with respect to T. So here is a differential equation. That is our complete circuit. We will use Raspberry Pi's 5B power to supply this circuit, and the circuit with NE555 is a square wave generator. We connect it to a differential amplifier to make the output signal more easy to process. Here is prototype of our circuit that we built on breadboard. Since we are validating our design, we didn't set our capacitor and resistor at correct value. Next, we will briefly introduce the Raspberry Pi. It is a single-board computer, and it's have 40 pin like GPIO, 5V power and so on. It can run a 64-bit operating system, so we can run Python on this device. It's a simple application of Raspberry Pi. Set the I/O port at correct mode and write some line of code. We can control the LED by pushing this button. Our environment is run on Pi OS 64-bit with Python version 3.8.6. We use tkinter to build the graphical interface. Its timer function will be called when it's received the clock signal. Note that some line will be modified when we connect to the circuit. And we design a button to make the program start. And the interface will styling to make it more easy to read. We will connect the circuit that we built previously by using GPIO API. We will use the 5V port and set up an input port to read the clock signal from the circuit, then add some modifications to the program to let the program call timer function when the signal is high-level logic. As for the result, our team shot a video to record the result. Let's watch the video.
So, this is the practical implementation of our circuit, and this is a stable multi vibrator. So basically, we use a stable multi vibrator. We use a 555 timer to generate a signal. So as you can see here, this LED, it's the output of this multi-vibrator gives this LED a signal so that it gets turned on and off. And this blue wire is the input signal of Raspberry Pi. So the signal generated by the timer will be through this wire. It will be transmitted to Raspberry Pi, and this green wire is the 5 voltage power supply, and this black wire here is the ground. So basically, we use this circuit to generate a signal, and this signal goes to Raspberry Pi. And this is the basic configuration of Raspberry Pi. So yes, as you can see here, this 5V power supply and ground and GPIO, something like that. So, and then I think we can talk about how Raspberry Pi works. So we use Python to write this code over here, and here we have this function that works when it receives a signal from our circuit. So here we have this setup. So this is a recursive function. So how it works is that whenever it receives a signal, the second plus 1, and then it just accumulates to a minute and an hour It's just like 60 seconds a minute and 60 minutes an hour. Basically, when the LED is on, it's true for the signal in our code, and when it is off, it is false for our signal in the code. So when the signal is false, here at this variable plus 1, and it accumulates to 60, and then this other variable minute plus 1, and then it accumulates to hour, and then hour plus 1. And here you can see this recursive function here. Basically, it just sees if it receives, it just tells if it receives a signal every 0.001 second here. 1000 is 1 second, so 1 is 0.001 second. And here we have this time sleep function, which means that it delays 0.2 seconds. Well, because here this recursive function cycles, it has a cycle of every 0.001 second, and since this period of time is too little compared to the signal pulse of our LED, so we have to implement a time delay of 0.2 second here, or there will be a malfunction of this clock. So, and now we can do a simulation of our clock here. You can see on the screen. Wait a minute. So, as I start this button, it just works as a clock and starts counting, as you can see on the screen. And you can see that it has the same period of time as the LED. So we can prove that this clock signal is generated by our multi-vibrator circuit here, because this on and off cycle is synchronized with our clock here. So here we made an extra function of our clock. As you can see, we implement a variable resistor here, and by adjusting the resistance of this resistor, I can change the period of my clock, and I can adjust my clock to a more precise one. So as you can see in this circuit diagram of our multi-vibrator, R2 in the picture is our variable resistor, and by adjusting that value, I can generate an input signal, a period of my signal that I want. So now we will do a little simulation of this extra function. As you can see here, this is a timer of my phone, and this is a precise clock. But here, the clock that we made with our circuit is not a precise one. As I click start. We can adjust the resistance of this resistor to make this clock faster. To catch up with the right clock. By adjusting the resistance, we can change the rate of this clock. And now we get a nearly precise clock compared to my phone here. Yeah, so here now we synchronize both the clock. So now I get my clock right by adjusting the resistance of the variable resistor.